Today we'll be working on the following problem. We want to construct a Borel subset E of R such that for every non-empty segment I, the Lebesgue measure of the intersection of E and I is bigger than 0 and less than the measure of I. Pause the video if you want to work on this problem by yourself. Okay, let's see what our solution is for this one. Solution. Okay, first we consider this. Let we collect all this open interval with rational endpoints. Basically, it's from a sub I to b sub I, this open interval, and then a sub I, b sub I, they are all rational numbers. A sub I is strictly less than b sub I, and I from 1 to infinity. Those are the countable collection of this open interval with rational endpoints, right? So now we want to find a sequence we want to define a sequence of sets, satisfy this. So let's say this is the first one, I sub I. So inside this, we find the two open interval A1, A2. And then we'll later on define what the properties for this A1, A2. And then for this, we also want find it to A sub 3, A sub 4. They don't have to be distinct. I just draw this, but they don't have to be disjoint, and they can overlap. And then for the K, also I say this interval, and then we want to find inside this A sub 2K minus 1, and then another one with A sub 2K, and so on, right? So this A sub I, the sequence, the condition we impose on this are like for any K, the length. Okay, let's use this, which is the we use some notation, the like the absolute value of A, which is the same as the Lebesgue measure of A, which is B minus A, where A is just the open interval AB, right? We use this notation. So for any K, so we want A sub K plus 1, the length is no bigger than 1/3 of the previous one. And then each A, 2K minus 1, and union A 2 sub K, this is contained in I sub K for any K, right? So this can be done because no matter how small the interval is, we can always make, A sub I is less than 1/3 of the previous one, and then we can even make it as small as possible, right? And then all we want is like for any I sub K, for this two, A sub 2K minus 1 union A sub 2K, this whole thing is contained in the I sub K, right? They can be overlapped. They don't have to be disjoint, but then we have this two condition. Now from here, we also define another set called for any K, so S sub K. So what we want is like from AK, we minus the union of I from K plus 1 to infinity A sub I. So basically we start with AK, but we minus all the following one. This to be our S sub K. So from this, because of this condition, why we impose this condition on A sub K is because we want this S sub K has a positive measure. And then from here, let's check this. So the measure, the bigger measure of S sub k, this is definitely because it's A sub k minus the union. This is because of the additivity of the measure, right? So this is bigger than m, the measure of A sub k minus the measure of the union from k plus 1 to infinity A sub I, right? This is definitely greater than or equal to m A sub k minus, because of the subadditivity, right? This sigma I from k plus 1 to infinity m A sub I. And this is also bigger than this, right? Because we have this, for any of this, the length is less than 1/4 of the previous one. So this could be this from AK. So the measure of AK times sigma I from k plus 1 to infinity 1/3, right? Times this. 3 to the I power, 1 over 3 to the I power, right? So if we calculate this, this is the geometric series. The sum is 1/2 A sub k, which is 1/2 of the measure of A sub k, which is greater than 0, right? Because the way like we make A sub k is a non-empty subinterval. So from here now we're ready to construct our our E. So the E, so the final E, right? From also we notice like for this, because Sk is any k A sub k minus this. So for any I is not equal to j, S sub I and S sub j are disjoint, right? Because one of them is appear in this sum. It will be removed, basically. And now also, like, we also know, like, also for any k, this union is actually a subset of A 2 minus A sub A, because S S of sub 2k minus 1 is a subset of A sub 2k minus 1 union this A sub 2k. From the construction, this is contained in I sub k, right? So now we define, now let our final E to be the union of all the S with even index. So S of 2k. And then at the same time, if we look at this set, which is the union of all S sub 2k minus 1 with the odd index, right? So from this condition, we know E and F are disjoint, first of all, right? And let's check this E is actually has the property that we want. So let's check for any open segment I non-empty, right? We have some k. So I contains I sub k, right? Because we can always find a open interval with rational endpoints that is contained in any non-empty open segment, right? So now if you look at the measure M of this I intersect E. Because of this condition, it's definitely bigger than M of what? 2K, right? M of S 2K, right? This is part of E. And then this actually contain what? And this is greater than 0, right? Because of this. For any K, we have the measure is bigger than this. And then also at the same time, for this I intersect F, same thing, is bigger or is greater than or equal to, for one contains IK, so it must contains F contains what? S2K minus 1, right? S2K minus 1. This is also greater than 0. But since E and F the E and F intersection is empty, so this tells us like this hence has to be bigger. This one is strictly bigger than 0, and because F is contained in the complement of E, right? Because this intersection, and then I with this. So basically we have this I, and then some E, some F. So then the intersection, because of this, greater than 0. So this intersection is strictly less than the measure of this open interval. That's it.